Welcome to this short recorded lecture, Lecture 7 for Math 5027. This is on the topology of a metric space, or at least it's our beginnings into topology. The focus of Lecture 7, these particular notes, is on the basics of a point set topology within a metric space. So we'll actually spend a few lectures on this. It will take us a couple of weeks to get through because there's a lot to unpack here. So one thing to point out is with the notation and language that Pew uses, which part of it is I refuse to use, is how he defines a limit point. So he essentially defines a limit point as any point in the space. Why even define a limit point then? So he says, well, there's other people, some mathematicians, I would say most, that require a limit point P to be the limit of a sequence of distinct points. And he says, well, we will not adopt that point of view. Well, I beg to differ. We will adopt this point of view. And so you need to keep that in mind when you're reading the text, that he does not. And so another word used in this context, like he says, if you're going to use the point of view that we are, is a word used by the French, which is adherence. Well, for his perspective, I've got another French word to describe that, and it's... So anyways, we will not be adopting his point of view. We'll be adopting the view of most mathematicians. Okay, moving on. He says a set S is closed if it contains all its limits. S is an open set if for each point P there exists an R such that the distance from P to Q is less than R for all the Q in a set S. And then he has this theorem about openness is dual to closedness, meaning that the complement of every open set is a closed set and the complement of a closed set is an open set. Meaning S is open if and only if its complement is closed. That's a good summary of it. So I'll start to kind of diverge a little bit from his presentation right away at the bottom of this first page of these notes and say, let's actually define balls and really start thinking about how we're going to define all of our points, limit points, interior points, isolated points, everything in terms of the relationship to balls in the metric space. So we're going to spend some practice in class actually drawing out what balls look like in different spaces, so with different metrics. So one thing I show here is what balls look like if you measure distance differently in R2. That's what this bottom example is. But first, the definition of a ball is defined by two things: a point in the space, which is the center of the ball, and the radius of the ball, right? So it's a pretty simple definition. Then the ball, denoted by B sub R of P, where he uses like a neighborhood to define this, and he uses another really ridiculous choice for the notation as far as I'm concerned, is here's the definition of the ball. It's all the points in the space whose distance away from the center of the ball is less than R. And I see I have a typo here, so I'll fix it before I post these notes. That point should be P. That is the ball of radius R centered at P. So there, I just fixed my typo, and I'll make sure that's fixed in your notes. And then I'm pointing out, hey, if you have the point P in R2, that is the origin, and you have a radius of 1, then what does the ball look like? Well, it depends on what you use for this metric D. If you use the usual metric, then you get a ball that maybe looks kind of like what you think a ball should look like a circle, the unit disk, right? But without the boundary. Notice the dotted line there, dotted curve. However, if you use D1, which is like the sum metric, so D1 is where you just add up, x1 minus x2 plus, that's I'm being so sloppy in my notation there, I'm sorry, y1 minus y2, where this is the distance D1 between, I would say, a point P1 and P2, where P1 is the coordinate x1, y1, and P2 is the coordinate x2, y2. So if you use that sum metric, what I also call the one norm metric, this is what a ball looks like. It looks like a rotated square. And if you use the infinity norm metric, the sup norm metric, take the difference of the individual components and take the maximum of these distances of the individual components, then you get a square that's aligned like this. So how you define the distance in a space is going to dictate a lot about what a ball looks like. So other useful definitions using balls in terms of points. So I define a limit point in terms of balls this way, and then you can show it's equivalent to the idea of a sequence of unique, distinct points that have to converge to it. So you should look at this carefully, but I'm saying that a limit point of a set S, so S is some subset of the space X, and a point P in X could be a limit point if for every single radius that you can think of, the ball of radius r centered at that point P has another point from the set that's not P. So what we're saying here is every point in the space is a candidate for a limit point. And then that point P might or might not belong to the set S. S minus P is S if P does not belong to S, and otherwise you're just considering the set S without P when you're taking this intersection. And we'll see examples of this, and in fact I have some examples below. A point P in a set S is an interior point, okay? So a limit point, any point in the space X is a potential limit point, and it's a limit point if it satisfies this criteria, then it's a limit point for S. But only points that belong to S are candidates for interior points. All right, so there's the difference there. And there what you're saying is there exists a radius greater than 0 such that the ball of radius r centered at that point P is completely contained in S, meaning all the points from the space X that it contains also belong to S. All right, so it has to be a subset of S. Now, a point P in the set S is an isolated point if there exists a radius r such that if you intersect the ball of radius r centered at P with S, you just get the point P. So again, points from the set S are candidates for interior points or isolated points. Points from the set S might also be limit points, but any point in the space X, those in S and those not in S, are candidates for limit points. You have to check if this criteria holds for them to see if they're limit points. But only points in the set S are interior points or isolated points. Okay. Then there's this property that, these other definitions, and this is more of a notation. We'll let S prime denote the set of all limit points of the set S. So you just collect them all and put them in S prime. And let S superscript 0 or superscript O, sometimes it's O, but I would say superscript 0, denote the set of all interior points. Maybe O is actually maybe a little lowercase o is better because it's like for the, you want to get to open sets. So that's probably why I should call it O. So we'll say O. Let S superscript O denote the set of all interior points of S. So I give some examples here and a question, and you should try to answer these, and we'll talk about this in class as well. And so if you return to the definition of open and closed that Pew gave, you could say that S is closed if and only if S prime is contained in S, right? So if S contains all of its limit points, that was the definition that Pew gave. And then S is open if and only if the interior of S, right? The set of all interior points of S is S. The S is only made up of interior points. So that's what Pew is saying. And so there's several different definitions of open and closed. They're equivalent, and we're going to prove their equivalence. So we're going to go back and forth between the different definitions that are equivalent as it's convenient to. So then there's this proof of theorem 5, and I do, I believe, both directions by contradiction. So I have assumed to the contrary here. So these are written out for you. You should read them carefully. I like to use interesting language instead of that's a contradiction, is to say things more like that's an absurdity or balderdash or kind of jumped around on me, or shenanigans, something like that. You can have a little fun, not much, but you're allowed to have a little fun when you're doing proofs. So I also outline that there's some things that are optional but good to have in the proof, since I'm often encouraging people to write as little as possible. But sometimes, I'm not against writing an extra sentence or two that's not necessary if it adds a great deal of clarity to a proof. So then we start getting towards this idea of letting T be a collection of open subsets. That's eventually something that we're going to be calling a topology, but we'll get more into that in the next set of lecture notes, lecture 8, that we'll probably be talking about more next week. I don't think we'll have time to start that in the week that we're talking about lecture 7. And what you're supposed to show is that if K is the collection of closed sets, so you always do this. They use K for closed, K is used for compact. I guess it's because C and K both make the K sound. I know that because I teach my son kindergarten in first grade in these interesting new times we live in. C and K make the K sound, and I've learned that. There's another word that makes the K sound. It also starts with F, and I think it's French. But But anyways, there's some other stuff for you to read here, but we'll just kind of move on. This page has a lot written on it. It's good for you to read. I don't want to kind of go over this in this lecture because this is a dense set of things for you to read and kind of sit with and let marinate in your mind and then ask me questions about. But I do want to get into this as a useful lemma. It's often given as homework problems, but it's something that we will prove and look at in class, which is to say if S is a subset of X, then the set of limit points to S is itself a closed set. And if you take the limit points of S union S prime, so you take all the limit points and whether or not they belong to S, you just put them back, you put them on S. That's the set of limit points there is S prime. And you can say, how do I interpret that? Well, I give you an interpretation. It's very important. This is a useful problem and useful conceptualization. The set of limit points for any subset of a space is itself a closed set. And if we add those limit points back onto a set, that's what this union's doing. It's saying, hey, take S and union it with all of its limit points to create a new set. So here's this new set, call it A. A prime, so the limit points of A were just the limit points of S. So you cannot create new limit points by adding limit points back in. And you're going to have to sit with that. We're going to do some examples in class. See if you can come up with some. But so we're going to prove it. We're going to do this definitely in class on whiteboards. Try it. Try sketching out how you think you would do it using the ball definitions that I gave you for what a limit point is, not what Pute says a limit point is. And think of an example where the limit points of the set of limit points is not the set of limit points, right? That's what this says. And again, you're going to have to kind of sit with these notations, and you're going to have to think of S prime as its own sovereign object, like a set B. It's a new set, and we're asking, well, what's B prime? What are the limit points of that S prime? So it can sometimes help just to create some, slight new notation to remove, multiple primes from the consideration, make it a little simpler to understand. And then the last page of the notes is to prove this. If S is a subset of X, then the closure of S is equal to S union S prime. In other words, we prove that S union S prime is the smallest closed set containing S. And if you said, wait a minute, closure, well, that was on this page I skipped over here. What is the closure of a set S? It's defined as the smallest closed set containing S. And this page describes how that's something that you can always define. But again, you need to read this kind of carefully because I get into some notions and ideas that are very important, but you need to spend time with. So that's it for this recorded lecture. Thanks for listening. I'll see you next week, and we will work on filling in all the details of these lecture notes on the whiteboards in class, and I'll also have additional examples and things put into that material on those whiteboards. See you next week.